Okay, I'm back. I just stopped the first video just because I didn't want the video to be 100 minutes long. Um, yeah, let's just get going on the rest of it. I'm not taking a break. Let's do the whole damn thing. Alright, so apparently this is a repeated linear factors problem. So let's factor and let's see if that actually turns out to be true. Numerator's fine, leave it alone. We never factor the numerator. In the denominator, I see that I can, if nothing more, I can factor out an x and then have x squared minus 2x plus 1. And then, yep, lo and behold, when you factor this, you'll have an x minus 1 and then another x minus 1. So there's your repeated linear factor. Now we'll write that as x times x minus 1 squared. And when we go to break that down, we'll remember that what we really have is 1, 2, 3 factors. So we're going to need 1, 2, 3 fractions. The first one will just have a denominator of x. The next one will have a denominator of x minus 1. And the third one will have a denominator of x minus 1 all squared. But again, remember, all three of these count as linear, right? They're all linear. This one just happens to be a linear to a power. But again, don't base your numerator on the expanded form of this. Base your numerator on just the power of the base. So this one's going to want a constant, so a. This one's going to want a constant, so b. This one's going to want a constant, so c. That is how you break this down. Now you solve it. And again, we solve it by multiplying through by the LCD. The LCD is going to be this expression here. Super psych. It's going to be that expression and an x. Alright, since I did that wrong, I'll stop trying to be a big boy and I'll just do it for real. We'll write it all out. So my LCD is x minus 1 squared and the x. So when you distribute that through, as always, this whole thing cancels and you just get the x squared minus x plus 2. Here we see the x will cancel, but we'll still have a times an x minus 1 squared. It's a fly flying in my face. Now with the b, one of the x minus 1's cancel, but you still have to multiply b by the x and one of the x minus 1's. And for c, both of the x minus 1's cancel, so you just get a c times an x. But there's that. We're now at that point where we make our decision whether we want to solve by systems or by let statements, and let statements are back because I do have these factors that have nice, clean, easy to find zeros. So if I let x equal 1, then a will be canceled and b will be canceled too, and I'll be able to solve for c. And then if I let x equal 0, then the b will be canceled, the c will be canceled, I'll be able to solve for a. And then it's a little tricky what we do to solve for b, but honestly it's not that tricky, so you'll see. Here we go. I'm going to go ahead and use the method of let statements. So we're going to say let x equal, and let's just start with 0. 0 is the easier one. So if we let x equal 0, then we plug into our quadratic and we get 0 minus 0 plus 2, so obviously just 2. Plugging in 0 here will give us a times negative 1 squared, which is 1, right? Which is going to be 1a. So this is a. And then this whole term cancels. Boop. And the next whole term cancels. Boop. And we're done. We just found that a is 2. So now, shrink. We will let a equal something else, or we'll let x equal something else. We'll let it equal the other 0, which is 1. Then plugging in the 1 gives 1 minus 1 plus 2, so actually it's 2 again. Yeah, this will be 1 minus 1 plus 2 is 2, so it'll be 2 equals, this guy goes to 0, so 0. This guy goes to 0 too, 0. And c just goes to c, because it'll be c times 1, so it's c. So again, we get 2 for c. So A is 2 and C is also 2. Now, the kind of tricky part is, okay, well, how do I solve for B, right? I got that question in class a bunch. And the answer is, we let x equal 0 because 0 would make these variables cancel. We let x equal 1 because it would make these cancel. But it's not a rule that says you can only let x equal values that make things cancel. You could literally let x be anything. If you wanted to let x equal like 14, you could. It's just letting x equal 14 doesn't exactly simplify this process. We would still have a live A and a B and a C, and that's not helpful. But guess what? We don't have A as a variable anymore. A is known to us now. So we could we could plug in 2 for the A, and then x could be whatever we wanted it to be. So what I said in class was, it makes sense to just probably let x equal just some simple, easy x value, like probably 0, right? If we haven't already used 0. Oh, we already used 0. So the next simplest number would be 1. We'll just let x be 1, unless we've already used, I'm faking it this time. First time was real. But since you've already used 0 and 1, the next obvious choice would be, okay, just let x be 2, and that'll be nice and easy to work with. And then the trick is, if you let x be 2, then you get, there's still an A, but not really, because you know what A is. So you let A equal 2 also. And letting x be 2 won't cancel out the C, but you know what C is, so you plug that in too. And so if you're plugging in an x and an A and a C, then the only thing left is going to be B, and we can find it. I hope that made sense. So we'll say let x equal to, why don't I build this right into the instructions? We'll say let x equal to, and substitute the A equals 2 and the C equals 2. Also, to get our new equation. That looks like one word, but I knew it was getting crowded over there. So what do we get? We're going to let x equal 2, so this will be, I'm going to do this the long way, by the way, but we'll go 2 squared minus 2 plus 2 equals, now the A is 2, so that'll be a 2, and x we said we're going to let be 2. That's a lot of 2's. Don't get confused. If it shouldn't be confusing, but if you really had a concern that A was 2 and C was 2, you could have let x be 3, right? It doesn't matter though. But it's going to be 2 minus 1 squared. Then B is our only unknown, so it's going to be B times 2 times 2 minus 1. And then C is not really an unknown to us. We know that C is 2, so you'll plug in 2 for C. And we let x be 2, so you'll plug in 2. That's a hell of a lot of 2's. Now just do the math. Forgive me. This will be 4. Take away 2 is 2, plus 2 is 4. This will be 1 squared is 1 times 2 is 2. This will be 2 times 1 is 2 times b is 2b. And this will be 4. So this looks like a 6 to me. So I'll subtract 6 and I'll get negative 2. And that'll equal 2b. And b will be negative 1. So we did it. Using let statements, we found A. Using another well-chosen x value, we found C. And then using literally any x value we wanted, and also using the A value and the C value, we were able to get the B value. So our final answer then is, it's going to come from, again, this decomposed thing. So A is 2, so we'll have 2 over A. 2 over x, geez. And B is negative 1, so it'll be minus 1 over x minus 1. And then it'll be plus 2 over x minus 1 squared. And there's our decomposed expression. So this big nasty thing, this quadratic over cubic, no, I pushed the button. Alright, anyway, that thing can be broken down to just these 3 simple expressions. It's going to be very useful when you get to calculus. Moving on. Alright, no header on this. but one would assume it's repeated linear factors again. We'll find out. Drink. Put that over there. So this is tricky sometimes too. You're going to factor out an x squared to be left with x minus 3. Yeah. I've definitely had people look at this and say, alright, well that x squared is a quadratic factor. But it's not a quadratic factor. That's a factorable quadratic. You could express it as x times x minus 3. So what we have here for sure is 3 factors. And all of them are linear. And just the x happens to be a repeated linear factor. If you treat the x squared as a quadratic rather than as a repeated linear, then you might get an expression that's equivalent to this, but it won't be in its fully simplified form. And so you'll get a lot of credit, but you won't get full credit. You'll lose points because you didn't break it down all the way. So let's make sure we're careful about that. So we can see now that from this factored form, we would want a fraction whose denominator is x. We'd want another fraction whose denominator is x, but to the power of 2. Then we'd want another fraction whose denominator is the x minus 3. And all 3 of these are linear. So in goes an a, in goes a b, in goes a c. And then you're multiplying through by your LCD, which is x squared times x minus 3. And that multiplies all the way over to here. So the entire denominator cancels, you get 3x squared. Let's go dark green. Wait, what am I doing? Oh yeah. Now it's a party. Get it? Party. Partial fraction decomposition. No, I spelled it wrong. Okay. Wish I could edit that out. Too late now. 3x squared minus 4x plus 3 equals. This is going to be an a. One of the x's cancels, but one of them lives on, and the x minus 3 lives on. Then the x squareds cancel, so I just get b. That same fly is back. I can't find it. I want to murder it. Then here the x minus 3's cancel, so we get cx squared. So there's our fully expanded form. This is our decision point. You could expand everything and build yourself a big 3x3 system of equations, but again, this looks like a really good let statement problem. We can let x be 0 and the a and the c will cancel, we'll get b. We can let x equal 3 and the a and the b will cancel, we'll get c. Then we can let x equal whatever we want and use the a and the c values to solve for... I think I said this wrong. No, I didn't. We need to solve for a. So we'd use our b value and our c value and any random x value we could find a. So let's do that. We're going to let x equal 0 first, I guess. Oh, actually, doing this is going to make my video look like a Khan Academy video. And you guys know I hate Khan Academy. Let x equal this then. Alright, can't go back now. So if we let x equal 0, then this whole thing on the left is just going to be 3. Letting x equal 0 means that whole thing goes to 0. This thing, though, will be negative 3b. And this third term will go to 0. So we just divide by negative 3, we get negative 1 as our b value. Then, do it again. White, I guess. White's a good color. We're going to let x equal 3. Alright, so this math's going to be a little harder this time, but 3 squared is 9 times 3 is 27 minus 12 plus 3. that's going to equal, this whole first term goes to 0 again. This time the b term also goes to 0, and the c term is going to be 9c. So what is this? Go away, fly. 15 plus 3 is 18. Equals 9c. So 2 is c. Pink slash. We've used, I guess we'll use, how's lavender on a black background? Yeah, it's not bad. Alright, so this time we will let x equal, again, literally anything. We already used 0, which would have been my first choice, so I guess I'll use 1 instead. So let x equal 0, and don't forget, b is -1 already, c is 2 already. Oh, I pushed the button. Oh, I still push the button. Okay, so let x equal then we're letting x equal 1, so we'll get 1 times 3 is 3, 3 minus 4 is -1, plus 3 is 2, so that'll be 2. Then a is the thing we don't know, but x is 1, so it's going to be, let me just do it the long way. It's going to be an a times a 1 times a -2, right? Then we know b. We're plugging in for b, so b becomes -1, and we're letting x be 1, so 1 minus 3 is -2. And c is known. We're plugging in for c, it's 2. And if x is 1, we're plugging in 1, 1 squared is 1. So here we are. We've got this 2 that equals -2a plus 2 plus 2. So that means 2 is equal to -2a plus 4. So subtract 4, and -2 is equal to -2a dividing gives +1 as our a value. I did not get the fly. Alright, let's go back to yellow for our final answer. So a is 1, so we're getting 1 over x. B is -1, so we're getting -1 over x squared. And c is 2, so we're getting 2 over x minus 3. And there's your final answer. These 3 partial fractions. What did we get before? Feels really similar. Yeah, it's pretty similar. We had 2 minus 1 plus 2. And this time we have 1 minus 1 plus 2. So pretty darn similar. Alright, hopefully this is making sense. Ugh. Alright. Let's keep going. Why is this here twice? Okay, so I'm not going to do 7 again. I don't remember what I did. Yeah, it's kind of worth doing, but I'm not gonna. But I think I was thinking about, I mentioned how if you factored out the x squared, it might be sort of interesting to see what we get if we do treat the x squared as quadratic. Maybe I am gonna do this. Alright, if we treated this as a quadratic, then we'd go ax plus b in the numerator. This one we would go c. I am going to do this. You guys can just fast forward the video if you're not feeling this, but I am doing this problem wrong, just to show you guys what will happen. So we would multiply through and cancel crap, would get our 3x squared. The fly. Alright, so if we multiplied through, we would get the ax plus b times x minus 3. The x minus 3 would cancel, you get x squared. Okay, fine. I guess let statements here still kind of work, right? Not really. If we let x be 0, we'd get an AB. If we let x be 3, we can solve for c at least. Let's do that. I've kind of mentioned that we can do sort of a hybrid approach to this problem, to some problems. So let's sort of do a let statement and let's also do systems, just so you can see. Because if we let x be 3, we can kill off the a and the b to have only c and solve for c, and knowing the value of c is quite helpful. So let's let x equal 3. Then we'll get what? 27 minus 12 plus 3. We already did this, didn't we? Yeah. This whole term goes to nothing. And then you have your 9c. So this is 18. So there's your 2. I forget that this is the same damn question, so of course we already knew that. But now, if we let x be 0, yes, this would cancel, but would still have an expression containing both a and b. So what would we do from there? Kind of nothing, right? We'd only have one equation. So really, to solve for this, we would have to use systems. But the good news is we already know what c is, so we can go ahead and just let c be something to sort of simplify everything. So I guess we're splitting this, and we're going back to the systems method now, so this will just be 3x squared. And we'll FOIL this out, so ax squared minus 3ax plus bx minus 3b plus cx squared. And again, you got a bit of a choice. You could plug in for c right now and just be treating this term as a constant term, or you can let it stay part of the quadratics. I'm going to let it just stay part of the quadratics. I'm going to fully write my system and then use the fact that I already know what c is. So quadratic term, a plus cx squared linear term, so negative 3a plus b and then our only constant is the negative 3b. So actually we don't really need much of a system, do we? Because if this is our only constant term, then we can get right to solving for b. And knowing c, we can get right to solving a. So this will be kind of a piece of cake. I'll keep going anyway. So we're going to have an a plus c that we know equals 3. We're going to have a negative 3a plus b equals negative 4. And then we have a negative 3 that equals 3. Sorry, negative 3b that equals 3. Alright, so we basically have everything we've ever wanted. This guy immediately gives us a b that equals negative 1. And then we could use the b value to find a here, or we could use our c value to find a there. I'm going to use it to find it here. So you get a plus 2 equals 3. So a is 1. So anyway, there you go. This is kind of that hybrid model that I've alluded to, where yes, I'm going to use one let statement to figure something out, and then to figure out the rest, I'll use a system. And already knowing even just one value makes solving the system so much easier, right? even if this equation down here hadn't been so easy, I'd have been able to solve for, I'd have been able to use C to find A, then I could have used the A to find B here and would still be done pretty easily. So the point is, though, the whole point of all this is now I go to write my answer, and my numerator up here should be 1x minus 1. So x minus 1 over x squared plus c, so 2 over x minus 3. And what I'm saying is, if you remember, that's just not fully reduced, because this was the answer we had before. Let me stick all that together. Then let me copy and paste. Alright, so again, the idea is these two expressions are totally equivalent, but if I'm telling you to basically completely reduce this thing as much as you can, then obviously the blue beats the black. So again, the analogy I was trying to make in class was to reducing just a regular fraction. If I gave you, whatever, 12 over 36, then somebody might notice that both of those numbers are divisible by 4, and then they're going to give you 3 over 9, and they're going to think, oh, what a great job I've done. And they did. They're not wrong. 3 over 9 is equivalent to that. But you can tell that you also need to be dividing by 3 to land on a fully reduced fraction of a third. That's kind of what happened here. We reduced this fraction down to the sum of 2 partial fractions, and that's better, but this guy here can still be reduced further by our process of partial fractions, and it would become these two terms. And so only the blue is really acceptable. Alright, cool. Was that worth my time? I don't know. If that was worth my time to really show you that, can you guys actually tell me? Again, you could leave a comment or just literally in class say, hey, Mr. F, I appreciated that you did that. That cost me 15 minutes of my life I'm not getting back, so if that was good for you, let me know. Moving on. Oh, hey, we did it. We're done. I think I said I would do these, though, and I will, because I don't know if we'll do these in class. This one's quite obvious. All you have to do is decompose this. You're just telling me how you'd set the problem up. So this would obviously be a over x minus 3. B over x plus 5. If you do not understand that, may God have mercy on your soul. Come see me for extra help. Okay? Next. This guy would get broken down into, well, alright, I mean technically this would be what? Negative x plus 2. You could factor out a negative, and then it's x minus 2. So I should, right away this is a little tricky. I'm not really sure what I would do here. I think I would treat this as repeated. I would call this an x and an x minus 2 that is squared, and you just also have a negative there. And what I could do is just sort of donate that negative to my numerator, make it a negative 5x minus 4. So then when I'm using my coefficients, I just let those coefficients be negative. But given that change, how big is this eraser? Alright, I guess we really want to break this down to 3. 1, 2, 3. One whose denominator is x, and then an x minus 2, and then an x minus 2 squared. All of which are linear, so A, B, C. But you kind of need to also make that notation that our numerator is going to change with it. We're going to have a negative sort of run through that numerator. But then from there we could do this problem and we would land on our best possible answer. Alright, I'm sticking with that. Number 3. This one's a little more cut and dried. The m in the numerator doesn't mean anything. You guys can ignore that. But basically you'll have a 7x minus 6. You'll have an x squared plus 9. And since this is an irreducible quadratic, we're good to go. This is a linear, so just put an A. This will be a bx plus c. But that's a fairly simple one in my opinion. Number 4. Is this factorable? Probably. Maybe not. Let's check. 3 times, I mean, it's definitely not actually, but let's really exhaust it. 3 times 9 would be 27. You're looking for factors of 27 that give you 7, and you're not going to find them. You've got a 1 and a 27. You've got a 3 and a 9. That's literally it. Those are the only factors. So this is irreducible. Since it's irreducible, we can just go to town. The only problem is we've also got this repeated linear. So that x cubed alone is going to generate 3 fractions. You'll have an x. You'll have an x squared. You'll have an x cubed. Then you've got this linear. You'll have a 5x plus 9. Then you'll have a irreducible quadratic, so 3x squared plus 7x plus 9. So we're going linear, 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 A, B, C. Then we're going linear again, D. Then we're going quadratic, so E, X plus F. But that's it. I'm saying that's it. I mean, that's a lot, right? That's what? That's 5 separate fractions. But, you know, I'm not asking you to solve from here. You just have to set it up. So there you go. I mean, this is a really good thing for you guys to see. We've got the repeated linears. We've got an irreducible quadratic. This has a little bit of everything. Next. Alright, so this one's kind of annoying. We've got repeated linear factors, and 5 of them. Then we've got repeated quadratic factors, 2 of them. So you guys should be expecting a grand total of 7 fractions here. So you're going to go 1, 2, 3, 4, 5. That'll tackle all these repeated linears. So x plus 4 to the 1, x plus 4 squared, x plus 4 cubed. This is tedious. X plus 4 to the 4, x plus 4 to the 5. Then you're going to have your 2 quadratics. So x squared plus 1 to the 1. And then an x squared plus 1 squared. And again, these guys are all linear, so you'll just go A, B, I need my plus signs. A, B, C, D, E. Then we get to the quadratic, so this will be F, X plus G. A, B, C, D, E, F, G, H, I. So H, X plus I. And I think I did that one in class for both periods, so you guys have seen this already, but this is it. You know, am I likely to give you a question like this on the quiz where all you have to do is set it up? Yeah, I'm pretty likely to give you that. That's a good little kind of warm-up question just to get you ready, and then I'll give you a couple more questions where you have to actually solve it all the way. Anyway, hope that made sense. Here's another one, another annoying one. I'm going to need a fraction with an x and an a. I'm going to need a fraction with a 4x minus 1. I'm going to need another fraction with a 4x minus 1 squared. But those are both linear, so that'll just be a b and a c. Then I got this irreducible quadratic, so I'm going to get an x squared plus 5 with a dx plus e in it. Then I got this other quadratic. And if this was a minus, then again we could factor, because it would be a difference of squares. But this is a sum, so it can't be factored. So you'll get a 9x squared plus 16. And you'll have an fx plus g. So neither of these quadratics were repeated factors. This was the only repeated factor. So you just get the x once. You get the 4x minus 1 twice, and the powers are 1 and 2. And then you get each of these quadratics only once. And there's your fully expanded partial fraction decomposition. And, you know, if you had to actually solve for A, B, C, D, E, F, and G, you'd likely be up a creek, because what would you get? You'd get the system of what? A, B, C, D, E, F, G. How many is that? 1, 2, 3, 4, 5, 6, 8. So you would likely have a system of 7 equations and 7 variables. Like, that's just not something you could reasonably solve by hand. So that's why we're not solving it. It's just not reasonable. 7. This looks easy. Oh, but it isn't. Curses. Alright. Hey guys, is this an irreducible cubic? No. Cubics are actually factorable. So, I don't want to do this. You guys remember 1,000 years ago, back in September, when we talked about how to factor this? We said that a sum of cubes could be factored down to the cube root, which is x, and the cube root of this, which is 1, and then the cube root of this squared, so x squared, and then the cube root of this squared, so 1, and then in the middle you have the product of the two cube roots, so x and 1. X times 1 is just x. Then we said that to fill in the sine pattern, we had our little SOAP mnemonic, SOAP, and that meant that for the first sign you use the same sign, so plus. Then you use the opposite sign, so minus. And then for your last sign, it's always positive, so plus. Now this whole thing was cubed, so that cube would apply to this factor and this factor. So the good news is now everything's irreducible. This is a repeated linear. This is an irreducible quadratic. And I know that just because the quadratic that you get from factoring a sum of cubes is always irreducible. So we are now looking at a grand total of 1, 2, 3, 4, 5, 6 fractions. We'll have an x plus 1. We'll have an x plus 1 squared. We'll have an x plus 1 cubed. We'll have an x squared minus x plus 1. We'll have an x squared minus x plus 1 squared. And we'll have an x squared minus x plus 1 cubed. Plus. It's times like these when I can totally understand kids who say they hate math. I mean, this is just tedious. Alright, guess what? These are linear factors, so they all just get an A, a B, a C. But these are quadratic factors, so these get dx plus E, and this one would get fx plus G, and this would get hx plus I. Yeah, that'll do it. There you go. Alright, then there's an 8. So this is factorable again. You got a oh, I don't know what to do with a factor of 2. Now we'll figure it out. But I do know that this will be x squared oh jeez, come on dude. X squared minus 4, x squared plus 4. And that's all squared. Alright, x squared plus 4 is irreducible, but x squared minus 4, that can be reduced. So I guess this is really going to be 8x minus 1 all over a 2 times an x plus 2 and an x minus 2 and an x squared plus 4, and it's all squared. Alright, so everything is now fully well, actually not quite. This 2, again, would have to affect all 3 of these terms, so I am going to take one more step, say x minus 1 all over. Actually, I should deal with this 2 as well. I'm not loving that 2. I'm not super sure what to do. I think, honestly, I might rather have a factor 2 in my numerator. So multiplying by 1/2 over 1/2 would essentially change my numerator into 4x minus a half. Maybe that's how I'd approach this. I'm honestly not sure. I'm not just playing dumb. I'm not sure what the best thing to do would be is. But I could kill off this 2 and just end up with 4x minus 1/2 as my numerator. Then I'd have a denominator of x plus 2 squared, so that's a repeated linear. I'd have x minus 2 squared, so that's a repeated linear. And I'd have x squared plus 4. So that's a repeated quadratic. So it looks like I'm staring down 6 fractions. That'll go to the a, or that'll just have a numerator of a. Then x plus 2 squared. That gets a b. Oh, what am I doing? That's not right. We're not going up to cubed. We're switching now to the x minus 2's. That'll go to the 1 and get a c. Then we go x minus 2 squared. That needs d in its numerator. Then x squared plus 4. That's quadratic, so it needs ex plus f and x squared plus 4 squared needs a b, c, d, e, f, g, x plus h. Alright, this has been great. Absolutely loving this. Okay. So we talked about this in class today. We said that if you're going to do partial fraction decomposition, you have to get the fraction into a form where the numerator's degree is less than the degree of the denominator. Right now this degree is greater. So the way we do it is by polynomial long division. So again, this is classwork, so I'm not going to do this one. Also, we did this one in class. Here's a homework problem. We'll do this one. So before you do anything to this, you're going to want to notice that the numerator has the greater degree, and that's bad. So we got to start off using polynomial long division. So we'll go x squared plus x. Technically plus 0, right? I don't think I really need that placeholder, but I'm going to put it anyway. X cubed plus 0x minus 2. This placeholder is more important. The one on the end is not that important. So we go x cubed divided by x squared, and we see we get just the 1x. Distributing that through gives x cubed plus... Oh. Okay. Forgive me. I'm dumb. We actually need 2 placeholders. 0x squared plus 0x minus 2. So we'll put the x up here, and we'll distribute that, giving me an x cubed, an x squared, and then nothing else. So we'll subtract. I mean, I guess technically there's a 0 here. So just to keep everything lined up nicely, these will cancel. We're subtracting this, so we'll get negative x squared. Subtracting this, we just get another 0. Do I bring this down now or later? Now? I'm getting tired, children. I don't remember. I'm not even sure. Maybe it doesn't really matter. We're going to get a negative 1, right? Because x squared divided by this one is whatever. So distributing the negative 1 gives negative x squared minus x, and then 0 again. Yeah, I think we want this thing down here. So we go ahead and do our subtraction. These cancel. We get a positive x. And then negative 2 minus 0 is negative 2. Yeah, and now we're done. we finally have a remainder because its degree is less. We've got our quotient. So we know that this thing can be rewritten as our quotient, the x minus 1, plus our remainder, the x minus 2, over the divisor, which is x squared plus x. So technically, we've just rewritten our expression in a simpler form. But this remainder over divisor thing, that can be decomposed, right? So we grab just this part now, and we're going to do the decomposition of just that part. Okay, I wonder like how much of this we could just do in our heads, honestly. So this is x minus 2. Let's see what we can get away with. We're going to let x equal 0. That'll let us get a. So if we let x be 0, then we get negative 2 equals a. And this cancels. So we've got our a already. Then we could let x equal negative 1. Negative 1 is going to give negative 3. And a 0 minus b. Right? Yeah. So if negative 3 equals negative b, then positive 3 equals positive b. So now we got them both. So our final answer is going to be sort of a combination of this stuff with the a and b plugged in, but this stuff too, don't forget your quotient. So our final answer should be an x minus 1 plus this thing, but in its partial, in its decomposed, its partial fractionally decomposed thing. So I shouldn't have said plus, I should have said minus. 2 over x. And then plus 3 over x plus 1. So there's that expression fully decomposed. You got an x minus a 1 minus a 2 over x plus a 3 over x plus 1. Okay? Hopefully this makes sense to everybody. You know, the first thing you see is us doing the polynomial long division just to get into the quotient plus remainder over divisor form. Then you kind of ignore your quotient and you take your remainder over your divisor and you just do the regular partial fraction decomposition stuff that we've always done. Yeah, and then you put it all back together. You then take your partial fraction decomposition bit and you take your quotient bit and you put them all back together to equal the original expression. Okay, there's only one more of these, which is great because 2 hours of making math videos in one night while I'm sick with a sore throat. This has not been my best life. Oprah would be very sad to hear that I'm not living my best life. All right. That's what Oprah says, right? Isn't that Oprah's thing? Live your best life? Or is that just generic? I don't know. You guys can tell me in the comments. We gotta do long division. Because even having degrees that are the same is bad. You gotta have a degree that's less. So minus 24x. Alright, obviously 5x squared divided by x squared is 5, so we get a 5. You distribute that 5. And you subtract. Cancels. This will be negative 24x plus 25, so 1x. This will be negative 32 plus 30, so minus 2. And that's that. We're in our quotient plus remainder over divisor form now. Our quotient is just the 5. And we're adding to that an x minus 2. x minus 2 over x squared minus 5x minus 6, which maybe we just factor right now to start setting the stage for the decomposition. So it's x minus 6, x plus 1, which means it is another easy one with just non-repeated linear factors. Again, you're going to ignore the 5. You're just going to deal with the x plus minus 2. Let's put a little dividing line. You can do the x minus 2, x minus 6, x plus 1. That's going to equal a over x minus 6. You're going to multiply through by the LCD. You'll get x minus 2 equals a x plus 1. And then you'll do your let statements. And I think the rest is cake. Alright, so if you let x equal negative 1, then you get negative 3. And it equals 0. What the? Oh, this is hideous. Negative 7b. So b is positive 3/7. Come on, Butler. Alright, that's fine. We should have an ugly one, I think. Then we're going to let x equals 6. Then dot 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 6 minus 2 is going to be 4. That's going to equal 7a's plus 0. So a equals 4/7. So then it seems to me that our original expression is going to be a 5. We got the 5 plus this thing in its partially fractionally decomposed form is going to be 4/7 over x minus 6. Plus 3/7 over what? X plus 1. Alright, again, this is unacceptably ugly. So you just hit this with a 7/7. And this one too. And so now you have plain old 5 plus. These 7's cancel, so you now have a numerator that's just a 4. And in your denominator you have 7 x minus 6. And then you have 3 over 7 x plus 1. And that is the final answer. Dear God, let that be it. There's no more, right? Phew. Okay. That's it. That's every single homework problem done. And it only took us 2 hours. Alright. Y'all better say thank you. Peace.